So there are possibilities of perfect boundary conditions. So you would have a perfect boundary condition of, this is a perfect boundary condition. So is this. So is this. Okay. So these are all can be called idealized boundary condition for whom you can very easily develop a differential equation kind of a theoretical solution, analytical solution. Okay, for all these boundary conditions. And I'm sure these have been taught already in your ASM course. Haven't these been taught? These have been taught, right? All these possibilities have been taught in the advanced structural mechanics course. Right? But often what happens is that you have to deal with a frame. So let's say, imagine a case, this is a column, but at the top, it does not have a boundary which can be idealized either as this or as this. You may at best be able to idealize it as something like this. And then you can say, okay, you can, again, it may be somewhat like this, or it may be like this, like so, or it may even be further down. Okay, and then you don't know what is here. So as you keep going on, keep going farther and farther, these boundary conditions options keep increasing and like keep diversifying more and more. So let's say I'm interested in this column's k value. So here I know that k value was equal to how much? What was the k value here?
2.
What was the k value here?
0.7.
0.7.
0.7.
0.7. What does the code say?
0.8.
0.8.
0. Yeah. So the code says 0.8. You can take 0.7 and theoretically 0.7, but the code, keeping some conservatism, it allows you to take only 0.8. But if we want to calculate k for this column, then we are in a bit of a trouble, because if I can try to simplify this column, here I can even imagine the fixed boundary condition, but at the top, even if let's say the lateral movement is restrained, if this is restrained completely, the lateral movement of this floor is completely restrained, okay, then I can say, okay, let it be a pin. But on top of the pin, the rotation is partly restrained, because when this column wants to rotate, along with this, the beams also, and this column also wants to rotate. Correct? So these beams and this column are going to offer some restraint, which rotational restraint, which in turn will depend on what is happening at the far end of these columns and beams. What is happening at all these locations, whether it is continuing again as a column or a beam, or it is getting fixed here, what kind of boundary condition you have. So basically you have some kind of a rotational fixity present here. This is a rotational spring. It offers resistance against rotation. Okay. Now the stability behavior of this kind of a beam will become more complex, and the stiffness of this spring, you can call it, what is the better term of stiffness other than K? I don't want to use K again. What else can we use? Let's say R. Okay, resistance. So that resistance of this spring is of course a function of theta, that is how much rotation you have to put, but also it is a function of what are the member sizes here, what are the spans of these members, what is happening at the far end of these members, all these things. Okay, and that is for the case when the lateral movement is restrained. What case is that? What kind of frame is it? If the lateral movement of a story is restrained,
Non-sway.
what do we?
Non-sway frames.
Non-sway or braced frame? Braced frame or non-sway? Yeah, the Indian code calls it non-sway frame. But you may also have a possibility, again, same column, this column, I'm just drawing again this column, which is again supporting some beams, another column, And now this time, the boundary conditions are such that it is free to move laterally. Okay, and the subsequent story again, whatever is happening here, is free to move laterally. Okay, and then any resistance against the lateral movement has to be provided by this column itself. Here, this column did not have to worry about the lateral movement. Only in the intermediate height it had to worry about the lateral movement. Here, this column has to provide the overall lateral stiffness as well. Similarly, for subsequent columns, they will do their own job, but this column is right now worrying about this one. Okay, sorry. Fine. So then there is a possibility of a lateral movement. So the column can actually bend like this. And then subsequently, these beams, etc., they can try to hold it in place. Right? So if the beams don't offer any resistance, what will be the K value? If you have a column like this, and then it is pinned here from all sides. Right? What will be the K value for such a column? You have a column, it is fixed at the base, and with the two beams and the top column, it is pin.
0.8, sir.
Who is it?
It's Leo.
Leo? No, it's not 0.8.
Okay, sir.
Anybody else wants to try? Fixed at the base, at the top, it's a sway column. At the top, it is pin.
1.2, sir.
No. It is this case, K is equal to 2. Cantilever. Was anybody saying this? K is equal to 2? I heard a couple of other students saying some noise, but I overspoke them. Yeah.
Her 0.7, sir.
1.5.
Sorry, 1% at a time. Who's at 0.7? Shayan?
Me, sir.
Shayan. Why is it
Yes.
0.7?
Sir, because one end is fixed and other is pinned.
Okay. Remember what I discussed just in the previous class? This is a sway column, right? Sway frame. What are the possible values of K for such a column?
K should be greater than 1.
Can you be a bit louder? I couldn't hear you. Is it Pujita?
Yes, sir.
Yeah. Bring the microphone closer to your mouth.
Yes, sir.
Yeah.
K is greater than 1. I think here 1.5, sir.
Okay. So yeah. So K should be greater than 1 only, and of course
Yes,
it can
sir.
go up to infinity.
Yes, sir.
Right. Now, why do you say it should be 1.5?
Because there is some fixity, even though there is sway. So I thought it
At
is
the
less
top.
than 2. Yes,
At the
sir.
top. No. So what I'm saying for this column is that the column's connection to the beam and the above column, which is not a very likely condition, but I'm just making a hypothetical condition, that all these three connections are pin connections. Then what is the K value?
2 only. It will be free
Yeah.
cantilever.
Then basically you end up with a cantilever only. Right? See, laterally it is free to move. Laterally this is free to move. Correct? Cantilever. This case.
Yes, sir.
This is free to move laterally. As far as rotation is concerned, it is free to rotate. When it deforms, it rotates this way. This is also free to rotate because the three members that are connected to this column at this end, they are all pin connected, so they cannot transfer any moment. So it is K is equal to 2. That will be an ideal condition of K is equal to 2. In fact, the column above does not really offer much of a resistance against buckling, because most likely what is happening is that even that column is also subjected to similar level of loading. So when this column is about to buckle, even this column will also want to buckle mostly. So actually what ends up happening is that this column does not really offer much resistance, because both of them are going to buckle out almost at the same time. They are equally close to their respective buckling limits. So in a sense, what you can say is that if the beams are pin connected to the column, you can pretty much assume K is equal to 2. Okay. For this particular column, in this part, non-sway frame, for this column, what would be the range of K values?
0.521.
0.5 to 1.
Yes. Correct. So K should be less than K should be less than 1, greater than or equal to 0.5, less than 1.0. Okay. So if no, that is true. So see, if the beams are perfectly rigid, absolutely rigid, they don't deform at all, then you will have a value of almost 0.5. At the base, you got full rigidity. At the top also, you might get full rigidity. So the beams have to be very, very stiff and rigidly connected. And if the beams are pin connected to the column, or if the beams are very flexible, the two things are basically same as far as this discussion is concerned. Either the beams here are very flexible, but you can't have a beam if it is very flexible. Beam has to offer some flexural resistance to the loads that are acting on the beam. So in other words, if you have some kind of a pin connection, right? So if you have a pin connection, no matter how stiff the beam is, it is not transferring any moment to the column, or it is not resisting the rotation of the column. It will not mind if the column wants to rotate. So in that kind of a situation, you are closer to 1, as long as the bottom is also pin connected. But here the bottom is fixed connected, so you will end up being closer to 0.7. If the top is pin connected and bottom is fixed, then you will end up with 0.7 or so. Okay. So this was the discussion from the previous class. Now, today we will go through the provision in the code, which actually describes how to calculate this R value. Okay, so this is not called R in the code. R is just one word I have given, which basically corresponds to the stiffness, rotational stiffness that you have at column ends, and that you need to use to calculate the effective length of the column. Okay. So we were somewhere here. We had discussed this provision wherein you apply some nominal horizontal loads. It is given in the Indian code. You go to clause 4.1.2 and you can find this description. It's not the complete description. There are some additional details about cladding, etc., but I'm not adding that. Generally, either you do this check, or the rule of thumb is that if the braces are provided of this kind, or very stiff rigid frame is provided, so like unusually rigid frame is provided with all welded connections, then you can consider it to be a braced frame, that is non-sway frame. Otherwise, it will be considered as a sway frame. Okay, so typical moment resisting frame systems are considered as sway frames. Now, let's say in a non-sway frame, I want to calculate what is the effective length of a particular column. So I need to know, of course, I need to know that the neighboring members are all connecting to that column rigidly. If they are not connecting rigidly, they are not counted because they are not offering any moment resistance, or they are not offering any rotational restraint. Only the members which are offering any rotational restraints will be counted here. Okay. So let's say we are looking at this column. At this column, at the top end of this column, you have 3 members offering rotational restraint because all 3 of them are connected rigidly. If let's say one beam was connected as a pin connection, then that one will not be offering any rotational restraint, and that will not be considered in this calculation here. Only one beam and one column will be considered. Likewise, at the bottom, let's say it is given as a fixed, then we don't have to do any calculation. So what happens here is that, let's say I want to calculate the K value of this beam. So first I need to calculate what is the fixity available at bottom end and what is the fixity available at the top end. Okay, and that fixity is calculated in these terms, beta 1 and beta 2, and you can switch between beta 1 and beta 2, doesn't matter. So let's say I call beta 1 at the top and beta 2 at the bottom. So when I get the value of beta 1 at the top and beta 2 at the bottom, I will use this chart between beta 1 and beta 2. And so let's say I somehow get my beta 1 to be equal to, okay, so imagine that this column is fixed at the base. Okay, so at the base it is beta 2. Fixed column has 0 value of beta 2 and perfectly hinged column has 1 value of beta 2. So fixed is 0. So here it is 0. At the top, let's say these are not offering much of a lateral restraint, much of a rotational restraint. So my beta is 1. So 0 and 1. So I'll be ending up with this line here, right? So, sorry, what am I doing? This is fixed here, and this is pinned here. So I should have something like 0.7, right? Yeah, so this is the point, and that's where effective length factor of 0.7 comes into the play. Okay, this is 0 and this is 1. Got it? And that's how you get, this is the point where the two interact. Or let's say the beta 1 value was turned out to be half fixity. So you got 0.5. So 0 and 0.5. So your value would have been almost, K value, effective length value would have been something like 0.58 or 0.59, something like that. Okay, that is this line, just under the line of 0.6. Okay, so that's how you calculate the effective length factor K. But I haven't told you yet how to calculate the beta value. So beta value at this end, for example, we are calculating. The idea here is beta is equal to summations of all K, certain K value. Again, that is another variable that we are adding. This is not the same K that is effective length factor. This is a new K. So K of all the columns divided by summation of all the K's of all the columns plus summation of K's of all the beams. What does this mean? This equation. What this equation is essentially saying is that on the top it is putting all the destabilizing members. So the members that are having a tendency to buckle. So this column wants to buckle, and of course the column above it may also be willing to buckle at the same time or almost at the same time. So you put all the destabilizing members at the top in the numerator. And in the denominator, you are putting all the members, that is both columns and both beams, which are likely to stabilize it. So of course, column would want to stabilize it or itself, plus the beams also would want to stabilize. But beams are not susceptible to buckling. That's why beams are not in the top, in the numerator. You followed me? So basically, it is giving, in a way, the propensity to buckle of a joint. Okay, we'll do an example and understand quickly. So there are subsequent steps in this. So moving backward, I want to calculate the effective length. For that, I need to know beta here and beta here. Once I know the two betas, I can use this chart to calculate the effective length. In order to know beta here, I have to do this calculation, wherein the effective the K factor of this, and this are calculated. 4 members are calculated. The 2 columns, their K values are put in the numerator, and both columns and both beams, their K values are put in the denominator to get the beta value. Now, what is this K value? This is not the effective length factor. The K value is Kc or Kb, either one, is basically equal to Ci divided by L. C is again a correction factor. We'll talk about it. I is the moment of inertia of this of a member that we are looking at, divided by length. Okay. Likewise, exact same calculation has to be repeated for a sway column also. The only thing that changes is that the chart here is different. So you calculate beta 1 and beta 2. Again, the beta values move from 0 to 1, wherein 0 represents completely fixed joint or absolutely no rotation at that end. And 1 represents completely free rotation at that end. Okay, so beta values vary from 0 to 1. And but the chart here changes. So earlier the value of K were varying between 0.5 to 1.0. Now the values vary from 1.0 to infinity. Okay, the rest of it is all the same. Okay, so basically what you need to do is, let me do an example. I think it's much easier to do an example so you can follow the steps. Is that fine? You have any questions directly from whatever we have discussed, or you can wait for the example and then ask questions? Anybody? If you have any urgent questions, you can ask. Otherwise, we can just go ahead to the example. Okay, so I'll go to the example. Then it might be easier to follow. So, since it's a kind of a lengthy process, unnecessary calculations, I don't like these kind of calculations very much. But that is what is there in the course. So we have to follow the process. Let's say this is the column of our interest in this frame system. And the frame is a braced frame or a non-sway frame. Okay, so this is a non-sway frame. Good. So how do we make sure that it is a non-sway frame? Probably what is happening is that somewhere at one of the base, so these are the two bases shown to us, but this must be extending, this building must be extending, and somewhere down the line I may have some kind of a bracing system in this building to hold the lateral movement or restrain the lateral movement of the beam of the building, something like this. Okay, so then this kind of system will provide you a non-sway behavior. Or otherwise, if the beams and columns are very heavy and you put them as a rigid connection also, that also can be used. So alternatively, you can make a very, very rigid, very stiff look, like in case of a PEB, those kind of rigid joints that we had discussed before. So sometimes they provide very heavy joints here too, and heavy joints and heavy beams. So these beams are much more stronger than what is required for gravity loads. Gravity loads may be very small, but still they provide very heavy beams to create lateral restraint. Some similar kind of a system has to be provided to create a non-sway, to make it a non-sway frame. So this is a non-sway frame, which may not be apparent from here, but it may be somewhere else through which it will be providing the non-sway characteristics to the entire frame. Fine. Okay. Now the member sizes are given: ISHB 400, ISHB 400, ISMB 600, ISMB 600. We only need these 4 members for calculation of K of this column. We want to know effective length factor for this column. Or effective length of this column. For this, we only need the member properties of these 4 members. Fine. At this end also, if there are any other members, then we would have needed this, this, and this also. But since this is a foundation already, we can assume a fixity of full fixity here. So we don't need the member properties there. Fine. We want to calculate KL, effective length for the column. And what it is saying is that somehow, for whatever way, this column is restrained against buckling in the lateral direction. So in out of plane direction, this column is not buckling, or even if it is wants to buckle, I am not interested in knowing the KL value there. So if I had asked you to calculate the capacity of the column or buckling capacity of the column, then you should have considered KL in plane direction, that is this direction of the plane of the frame. That is what we will be calculating now. Also the KL in the other direction, and whichever one was smaller, that would have covered. But in this particular case, you are simply asked to calculate the KL value of this column for buckling in the plane of the frame. So you don't have to worry about the other KL. Okay. Also, one value is given, that is the load on the column is 7560 kilonewton. Now that might be a curious information for you. Why do we need the load? Because for calculation of KL, all we should have needed was what members are there and how much rigidity they are offering. You will see that in the process, when you calculate C, there was a factor called C here, right? This effective length factor, depends on betas. These betas depend on KCs. These KCs depend on CI by L. So yes, I and L play a role. I is the moment of inertia of different members and L is the length of different members. But C here also depends on the load acting on each member. The reason for that is that if a member is a column and it has a heavy load acting on it, its rotational rigidity will be much lower than a beam if it's not having any actual load acting on its column, on it. Okay. So that's why this information is provided. What is the load on that member? Okay. So we will start solving this problem. So we want to determine the KL for the column in the ground floor. The total height of the column is 3500 millimeter. Okay. And the load is given as 7560 kilonewton, 7560 kilonewton. Okay. ISHB 400, that is this section. ISHB 400, that is the columns. The two columns are same, ISHB 400. And the I value I have taken and corresponding R value I have taken. These are both in the plane of the frame. Okay. This is not in the out of the plane direction. Similarly, the beam, again, in the plane of the frame, that is when this beam wants to bend this way, in the major axis, because if you can see these lines, these clearly reflect that these are the flanges. That means this I is in the major axis. Likewise, for a column also, this I is in the major axis or strong axis. Okay. It could also have been oriented differently, but I have considered it with this orientation. Okay. So now we want to calculate what is the effective length. So what is the first step? I have to calculate beta here, and I have to calculate beta here. So beta here is involved. So first let's calculate beta here. So this is a fixed boundary condition, right? So for a fixed boundary condition, and it's a non-sway frame. So we will go to this chart. This is for non-sway braced frame. This chart, one beta I need to calculate. I will find it out, but the other beta I already know is fixed. So if it is fixed, that means my beta value there is 0. Okay. So I know that my beta value for this column's bottom is 0. This beta is equal to 0. The beta at the top end I have to calculate. And what will be playing a role here? The beta at this end will depend on how much fixity this column offers, how much fixity this beam offers, and this column itself offers. And also how much susceptibility to buckle this and this columns have. Okay. So beta 1 will have in the numerator the k values of the two columns added together. And in the denominator, it will have the k values of all four members, two columns and two beams. Sigma kc, sigma kb, two beams and two columns. Okay. K for any given member is equal to ci by L. I and L is straightforward. What we need is C value. And C here is actually given in table number 35, which is a function of n bar. So now let me take you to the IS 800. Yes. So this is the clause, annexure D. This is not part of the main code. It is a part of the annexure only. So this is how you calculate the effective length factor K. Okay. These two. This K and let's see if I can get it. So this is 1K. This is for a sway frame, this is for a non-sway frame, the K value. And this depends on beta and beta 1 and beta 2. You can also use, instead of this equation, you can also use these charts if you know the beta 1 and beta 2 values. Okay. Beta 1 and beta 2 respectively are given by this equation. Here there is a mistake here. This should be sigma Kc. Please make this correction in your code. Is sigma Kc divided by sigma Kc plus sigma Kb. That C is missing at the top. Fine. And then K for any value, for any member, this particular K, not this K. So this is silliness of Indian code. It uses this K, and then one may be confused that this is the K that is supposed to go there, which is wrong. This K and this K are not the same. This K is supposed to be here. Okay, so the Indian code is not written in a very professional manner. They should have used different variables for this K and this K. Okay, so the K here that is supposed to be used here is actually equal to Ci by L. Okay, and I by L is obvious. It's not that difficult to find. I is the moment of inertia of the member. L is the length of the member. C is the correction factor, and the value of C depends on two things. One, it depends on this n bar variable. The value of C or other three things it depends on. It depends on whether it's a braced frame or an unbraced frame. Then it depends on the far end, whether it is pinned, rigid or fixed. Pinned, rigidly connected to a column or fixed. So what is happening at the far end? And also it depends on n bar. N bar is basically representing how much axial load is acting on that member. So on a beam, typically you can assume that there is no axial force acting. So when you are trying to calculate Ci by L for a beam, Okay, what will be the C value for a beam here? C depends on this equation, wherein one of these parameters is n bar. Let's say I want to use this formula for a beam. Okay, so what will be the n bar value for a beam?
0.
Yes,
0.
n bar for a beam will be 0 because n bar is basically P divided by PE. P is 0, therefore n bar will be 0. But for a column, that won't be the case. And PE is nothing but pi square EI by L square, elastic buckling load. Okay, now coming back to this. So what we will do is, we want to calculate what is the effective length of this column. So for the effective length calculation, I need to know beta. For beta calculation, I need to know K of these members, this, and this. Okay. For K, I need to know C. And for C, I need to know n bar. So let me start with calculation of n bar. So first I'll calculate n bar for this column. And n bar is nothing but actual load acting on the column divided by the elastic critical buckling capacity of the column. That is P divided by P critical, or P divided by PE. Okay, so this was the load acting 7560. And this is the pi square. This is E value, pi square E, I. This is the I value divided by L square. That is the length. Okay. Now you may ask, how do I know the length already while I'm still trying to calculate the effective length? Well, I mean, you have to start with some value. So you start with assuming that K is equal to 1, and you start with this value. Okay. And you get n bar. Now the question, of course, can come, should I reiterate it? You can reiterate, it won't make huge difference, and that's not really the purpose of this exercise. So just to so you don't really have to reiterate it. So after you get a new KL at the end, you should not, the question may be asked, should I go back and correct these values again? You may or may not. Okay, so you got n bar for this column. Likewise, you can get n bar for the column above. What will be the, so for this column, the column in question, I got n bar is equal to 0.167. Okay, what will be the n bar for the column above? Geometry is same, length is same. Okay. What does it depend on? It depends P divided by P critical. So P critical is same, right? Because we are not accounting for the boundary conditions as of now. Pi square EI by L square. So I is same, and also the load is same because both columns are carrying almost the same load. Now, I mean, truly speaking, this column will be carrying less load than this column, but you can imagine that these columns are a part of a tall building, and the loads are almost uniform across the floor. Okay, so in that case, this column will also have an n bar of 0.167. Now the beam, the two beams are identical. This beam and this beam are the same. So you can assume that their n bars will be equal. What will be the n bar? P divided by PE. P is 0. There is no axial load acting on these beams. Beams are not generally meant to resist the axial load. So P is 0. Therefore, n bar is 0. So n bar is 0. Here also n bar is 0. Fine. Now, after n bar is calculated, now we want to know what is the C value. So, if you go to this table, erasing it is a very, very hard thing. In this table, table number 35, the correction factor C, it depends on n bar, but it also depends on what is happening at the other end, and it also depends on whether the brace is frame is braced or not. So yes, this frame in question is braced. So we are restricting ourselves to this column. We are not going to use these values, only these values. Then among these values, whether the far end is pinned or not. So I'm looking at this column right now, right? This is this column, and I'm looking at the beta value here. So what is the far end? This end is the far end, correct? So the far end of this column is either pinned or fixed or rigidly connected to another column. So is it pinned or fixed? It is fixed. So since it is fixed, I can use 2 times 1 minus 0.4 n. 2 times 1 minus 0.4 n. Okay, and I can substitute the value of n bar here, and I'll get a value of C. And then Kc will be equal to K for this column will be equal to Ci by L. C I have got 1.867. I already know for this column, and divided by L. That is this much. Now moving to the column above, we had calculated n bar for this column. The C for that column. Now I'm looking at this column, but beta value here. Okay, so since the beta value here, the far end is this one. At the far end, what is happening to this column? Is it pinned at the far end? Is it fixed at the far end, or is it rigidly connected to another column at the far end? It is rigidly connected to a column at the far end. So n plus braced frame. So I need to use 1 multiplied by 1 minus n bar. That's what I use here. And I get the C value of 0.833. Then for Kc, I calculate C. I is same as here. The two i's are same. Similarly, the same length L. I get a value of Kc. Okay. So if you can see here, what is happening is that the restraint effect, the Kc effect of this column, or I'm calculating beta here, right? So from this end, it is getting more restrained. So Kc here is higher for this end, but for this end, from this end, the K is smaller, okay? Because that end is free to is easier to rotate than the fixed boundary condition. That's why. Then for the beams, again the same calculation has to be done. N bar we had calculated was 0, and the beam again, the far end for this beam is this is the far end. For this beam, this is the far end. So for the beams, the far ends are again connected to columns, rigidly connected to columns. So if they are rigidly connected to columns, I can take 1 minus n bar, and n bar was 0, so I get C is equal to 1, and then I substitute them in the K value. So C I divided by L. Now beams are 6,000 mm long. Okay, so Ci by L, and I get this much of rotational restraints coming from the beam. Now, once I know the Kc's and Kb's, I'll substitute for beta. So beta 1 will be equal to the values of the columns. So one column was giving me 149, the other column is giving 66.9, 149, 66.9 divided by 149, 66.9, 153 and 2. Okay, why multiplied by 2? Because there are two beams. Otherwise 153 plus 153. What I get is beta is equal to 0.42, and beta 2 was already calculated as 0. So beta 2 was 0. Beta this comes out to be 0.57. Sorry, 0.42. Now for 0 and 0.42, I need to get K value. I'll use this chart. This is the chart for braced frame or non-sway frame. One side is 0.42, the other one is 0. Okay, so somewhere here the value of K will be more than 0.757, but less than 0.6. So you can say 0.58 or so. You have taken it as 0.57. You can take it as 0.58 or something. Hardly matters. 0.42. Yeah, 0.42 will be like this 0.575 is actually for a value of greater than 0.4 here. Something like that you have to go. Okay. So at 0.42 will be very close to this line, in fact. So that is calculated as K is equal to 0.57, and the effective length will be 0.57 multiplied by, I've taken clear height here. That is usually the practice. Then the effective length will be, so even though the actual length, total length from floor to floor was 3,500 millimeter, here only the clear height is taken. That is 2,900. So the effective length will be 1,600. Okay. Now you may ask, why did I not take 2900 here? You could take that also. It doesn't matter. It won't change things drastically. Okay. So effective length turns out to be 1600 millimeter, 1653 millimeter. Now, is the process clear? I would recommend you go through this exercise again and go through the textbook also. Textbook also provides you a few examples. Okay. Then you would have a better understanding of the process. Fine. Any questions?
Sir,
Yeah.
in this problem, the governing a plane of bending should be out of plane because
Yes. Yeah, that must be the governing one, but this is just a theoretical example, of course. Yeah.
like while we design, we'll go for the minor axis bending.
Yes. See, the thing is that when it comes to minor axis bending, then you have to worry about. In steel, it is more complex. That I had mentioned that in the previous class. In concrete, this is a very common practice to do. In steel, relatively, it is uncommon. Couple of reasons. One is that most of the frames are not rigid frames. Most of the frames are pin-connected frames. That is, the beams are not rigidly connected to the columns most of the times. Only at a few locations you do this, where you connect the beams to the columns rigidly. That's where it is applicable. If it is already pin connected, then that issue does not arise, and you can take the K value as 1. We discussed that today, correct? If the beams are connected to the columns as pin connection,
Yes.
and so maybe the ground floor one, you may not be able to take that as 1 effective length factor. For the subsequent floors, you can take it as 1. And in fact, for calculations, easiness of calculations, they take K as 1. See, what happens is that when you are talking about, see, in this entire calculation, you had a column, then you had 2 beams, and these beams were offering resistance against rotation to the column. Now imagine at the same time, when in the same setup, you already have beams in the out of plane direction. Okay.
Yes, sir.
Now those beams also might be offering a resistance, and then but in steel, what happens is that when this connection wants to rotate this way, these beams will be undergoing torsion.
Okay, sir.
So we ignore that contribution that is coming through it. But if there is a slab also which is connected to those beams, and then those beams are trying to go into torsion, then that slab will be undergoing bending.
Yes, sir. Okay.
And then it becomes more complex. So this kind of an exercise is relatively less common in steel. But nowadays, I have seen several structures where the connections are all done through welding. That means that makes the connections rigid. And if that is the approach the designer has taken, where all the connections are welded connections, they are all rigid connections completely, hardly any bolts are used, then in that case, you have to think of this possibility. Therefore, this chapter is covered. But otherwise, see, in IS 456, this is very predominantly taught. And I'm sure this entire chapter will be taught in a lot of detail in your advanced concrete course. Those of you who are taking or who have taken this advanced concrete. Has anybody taken advanced concrete already? No.
Yes,
Rohit,
sir.
you have taken it, right? So,
There it will be explained, sir.
yeah. So again, the same concepts will be explained in a lot of detail. And the reason for that is obvious, because rigid beam column connections, monolithic beam column connections are much more common in concrete. But in steel also nowadays, because people don't want to deal with bolted connections, welding is found to be much more, I mean, it was not so before, but nowadays I can see that welding is much more prevalent for various reasons. And for that, reason, the connections are getting rigid, more rigid. And because of that, this becomes relevant. So you should be familiar with this kind of a concept. Okay. Did I answer your question? I mean, I was talking
Yes.
for a very long time.
Yes.
Yeah. So to answer your question, yes, you are right. It should be the minor axis buckling that should be critical. But what happens is that when in a minor axis, typically your connections are not rigid connections. In steel, again, not in concrete so much. In concrete, you don't have a big difference between in a column especially, you don't have a big difference between minor axis and major axis. Sometimes you do, but not necessarily. But in steel, that is very clearly evident because you have flanges. And if you have flanges, then one major axis is much, much stronger than the minor axis. Now, let's say I have an I section, and this is the web of the I section. You can see my hand. This is the web. You have one flange here, one flange here. It is much more easy for me to provide a rigid frame in this plane. But providing a rigid frame in this plane basically requires me to connect this member to the web of the column. And that connection is not easy, because if I just connect to the web, it will not really be rigid. The web will be undergoing a lot of deformations. So then I have to make a very complicated connection here to make it behave like a rigid connection. So they usually avoid that. So in minor axis, most of the times you will not have a rigid frame. You will have rigid frame only in the strong axis. So the columns or beams and columns will be oriented in such a way so that you have a rigid frame only in the strong axis.
Yes, sir.
Does that answer your question? Maybe I can quickly draw something also. It's an interesting point, and this is actually, it comes from design practices more than the fundamental concepts. So if I'm looking at a building here, plan of a building, okay? So you have, let's say, these 9-column building, okay? And I'm looking at the building from the top, and this is the footprint of the building, if you may say so, okay? And these are the 9 columns. Now imagine these 9 columns, I want to make them as a rigid frame on the outside at least. So what I will do is I'll put 1 column here, put 1 column here, put 1 column here. Okay, these are all I sections. Now, of course, here also I'll do the same thing. Sorry for me being lazy. Actually, I should have erased these circles, but I hope it's not too much of confusion. Now what happens is that this is fine. So now I can connect beams between these columns and make them rigid frames. So I can rigidly connect these beams to the columns, right? Because I have got flanges of the columns connecting to the beams. So flange to, this is the column. This is the column flange, and the beam is coming and meeting it here. And I can very easily weld, or you can, I can, like, there are hundreds of ways in which I can provide this rigid connection between the beam and the column. I'm just showing you one. So I can weld the flanges of the beam to the flanges of the column. Perfect. That is rigid connection. If I have some doubts about the rigidity, I can put some stiffeners here. Okay, and that will give me the enough rigidity. Or if I have any additional doubts, I can also put another stiffener here in the column. Okay, so that is typical detailing of a rigid beam to column connection. But if my column was, so this column from the top will look like this. Correct? This connection will look like this. So this was the beam. This is the column. And the flange of the column is connected to the flange of the beam. Now, in this direction, what do I do? The challenge here will be, I want it to be a rigid connection or a rigid frame. So the column has to be oriented this way in the major axis so that it offers any resistance to the lateral load. If I apply a lateral load in this direction, the column has to be oriented this way. Now, this part is fine. The beam can be brought here all the way to the column. It can be connected nicely. Here it is fine, but here it is questionable. What will happen here? Imagine the same column, same beam, looking from the top. Let me erase this part. So same column, same beam. Here, this part was fine, but in this direction, what is happening is that my beam is coming this way. Okay, and now sometimes the beam may not fit inside the column, but even if it does, even if it fits inside the column, is able to come within these 2 flanges inside. How do I connect this beam to this column rigidly? One way is to again connect the flanges of the beam to the column. Now I'm looking from this side. This is the column flange. This is the web inside. Okay. Let me go into the column. So this is the web of the column. Okay. Now the beam has come here. If I weld this beam to the web of the column, the web is very thin usually. So once I apply any kind of a moment demand here, the web is simply going to bend and it will not offer much of a resistance. And strengthening the web is much harder. because the kind of elements that you had available before, that those are not available with the web. So the web is very weak in this axis, and you cannot provide a rigid connection with the web. So you have to devise a very complicated connection here and effectively make a box of sorts around the column, then connect the beam to that. So this is never done, hardly ever done. So we don't provide a rigid connection in the minor axis of a column. Okay. I hope I didn't take too much of time and I actually was able to explain what you were asking.
Yes.
Right. So therefore, that question does not arise about minor axis so much, because in the minor axis, mostly the connections will be pin connections. Okay. But yes, when you are looking at the effective load capacity of a column, you should be looking both about the minor axis, major axis. For major axis, you have to worry about these restraints also. In the minor axis, mostly these restraints won't be available because the connection themselves would be typically pin connections. Okay. Moving forward, so we had I had talked about flexural buckling before, and I had kind of alluded to this idea that flexural torsional buckling also exists for members, especially for the members which are asymmetric, right? So, but I had said that angles like what is shown here, even if it's an equal legged angle, the two legs are equal, it has a one flexural mode of buckling, that is about VV. This is a singly symmetric cross section, right? So about VV, that is the smaller or weaker axis, the axis that is not of symmetry. About this axis, you have flexural buckling possibility. About UU, you don't have a pure flexure. So what you have is two modes of buckling, about which both of them are a combination of flexure about UU and torsion. Okay, but that's not what the code recommends. The code allows you to use for an angle that is loaded concentrically. You have to be very careful about this phrase. Loaded concentrically. So first you have to find a way how to load it concentrically. If somehow you are able to do that, then the code says that typically the bending will take place about VV axis, but somehow if VV is restrained, then it will be taking place about UU axis. And it gives you the R values for both UU and VV axis. RV is much smaller than RU, that's why it will be taking place about V axis. But if V axis is not possible or for some reason is restrained, then it will take about U axis also. But you should use buckling class C for angles. Okay. Why does it do that? Why does it allow you to use UU axis also? That is just for easiness of calculation, and they might have seen that it does not really make a huge difference whether you explicitly account for the lateral torsional, the flexural torsional part of it. So simply by using flexural buckling equations of class C, you can calculate the capacity. Okay. However, that is not how most of the angles are really loaded. Most of the times, the angle members, right, are loaded only through one leg or connected only through one leg. So if the angle is loaded or connected only through one leg, and typically on both sides it's the same leg, then you have the issue of shear lag that we have discussed in detail in tension members. So, or shear lag, or in this particular case, we can call it eccentricity. Then basically the possibility of any kind of pure flexural buckling can be completely ruled out with the eccentricity coming into the picture. And then the code says that you can actually, you have to account for flexural torsional buckling. But funny thing is that you can still continue to use the same equations. Which same equations? Same column capacity equations I'm saying. Class ABC column equations were given, right? These ones. The same column equations you can use. In fact, you should use class C column equation for an angle that is connected only through one leg. If an angle is connected only through one leg, you consider class C here, which is actually a flexural buckling equation, but the lambda value that goes into the calculation of that curve changes now. Okay, and that lambda is modified in such a way so that it incorporates the flexural component as well as the torsional component. So if you see the equation of lambda in this case, it is not regular lambda, it is lambda E, which has terms of some constant which depends on the boundary conditions. Some other constant multiplied by lambda VV square, which is flexural term, lambda flexural. And here there is another lambda, which is lambda torsional, lambda phi. Okay, and if you look at the expression for lambda phi, you see some terms which are associated with torsion. Okay, so when if you are being taught torsion right now, or you will be taught torsion in advanced structural mechanics soon, then you will see that you deal with torsion, these terms b1 plus b2 by 2t for torsion constant of angles. Okay, so this is in a way a torsional term, lambda phi. Lambda vv is flexural term about vv axis, and then combined you have an effective lambda. And then also there is a mistake here. It is marked as epsilon here. So there are two epsilons in this equation, one outside the square root sign, one inside the square root sign. Let me take you to equation 7121 in the Indian code. Yeah. So this is the code. Here you can see there is an epsilon outside the square root sign, and there is another epsilon inside the square root sign. So this epsilon should actually be E. This is a typographical mistake. So these are actually E values, and epsilon we have already discussed in the past. This is basically to prevent buckling before yielding, local buckling before yielding. Okay, so you calculate lambda VV like from this equation, which is again all the terms are self-explanatory, I divided by RVV, and lambda phi, that is again geometric properties are there. But in addition to these, the factors K1, K2, K3 have to be calculated, and the values of K1, K2, K3 are given based on the rigidities at each end. So whether how many number of bolts are used at each end based on that, and then if it is a gusset plate or if it's another member to which it is connected, what kind of fixity it offers. Based on that, you may pick the value of K1, K2, K3. So typically a gusset plate is considered to be very rigid in its plane. So you can, if there is a gusset plate, you can take it to be fixed. You can simply use the values from here. So if there are 2 or more bolts applied, and if it is connected to a gusset plate, you can assume it to be, you can take the values 0.2, 0.35, and 20 for K1, K2, K3 respectively, and plug them here, calculate the lambda E. Once you know the lambda E value, then you simply go to this equation or this plot. Yes. You can simply go to this plot, which is between lambda and FCD. So you can simply use this at curve C to get the FCD value. Okay, is that clear? Any doubts about this one? Any questions?
Hello, sir.
Yeah.
Sir, what is that I divided by R VV? What is that that term?
Okay, let me check. It should not be I. Let me check. Maybe I made a mistake here. It's length actually. L. Sorry. Yeah, I mispronounced that. It's length of the member. L divided by R.
Okay.
Yeah. Why should it be I? Yeah. Thank you. Thank you for pointing it out. Yeah. So this. Let me repeat it for the interest of the class. This I had called I. It is not I. It is L. It is the length of the member. Okay. Anything else?
Sir,
Hello.
Yeah, one person at a time. Lohit?
sir, I have a generic question. Sir, normally when I was going through literature, so I found that tubular sections or circular hollow sections are the most efficient section for compression members because more amount of material is distributed for their RX will be very high. So,
Yeah.
but generally when we see for any steel buildings,
Yeah.
generally even while you are explaining, you took only I sections, but not
Yes.
that RX sections. Can you
Yes.
explain why?
Yeah. That's absolutely true. Hollow tubular sections are very efficient because the most of the material is placed farthest away from the centroid, especially when it comes to compression. Because you don't know which axis it's going to buckle. So perfectly true. The challenge with I sections is the connections. So challenge with the tubular sections is the connections. How do you connect them? So and that is why I sections and angles are particularly very popular. because you get so many flat surfaces which are at 90 degrees from each other. They provide you so many places to which you can weld or you can bolt things together. Yeah. So it is not just the theoretical understanding of load, the way loads are taken. In field, when you have to put them together, connecting them together, for that you need to find flat surfaces to connect them together so that it's easy to provide. For tubular sections, there are some for relatively less significant structural systems. Tubular sections can be used easily. Also, when the projects are very, very high profile, then again tubular sections can be used. So you may see the use of tubular sections in. Can somebody tell me, or Lohit, you can try. Where have you seen the use of tubular sections more predominantly?
I mean, cast, when they mix the both composite sections, then I have seen tubular composite.
What kind of composites you are talking about?
I mean, both RCC and steel. I mean, for rapid construction, generally they use. I mean,
steel concrete composites. You are saying so? Steel beam concrete slab. Is that what you are saying? Or
no, sir. I mean, if a column want to be constructed, then
okay, yeah. So that is very different type of an application.
Okay.
That is for a column. So, and plus, once you are filling it with concrete, those worries are kind of like already addressed. So that is not what I am talking about so much. So any other places where you might have seen, especially where the trusses are involved?
maybe airport hangars.
Yes.
Airport.
Yeah.
hangars.
So not so much in hangars, maybe in hangars too. So where I have seen mostly, especially airport, those big lobbies, right? So they make these roof trusses or stadium, etc., where they make these roof trusses, which are made of 3 big pipes, which are curved, and then internal braces are also pipes sometimes other members, but mostly pipes. So what happens there is that mostly these things are developed in a factory. Those entire truss, the entire roof truss is built in a factory, and a lot of continuous welds are required. Maybe I can try and draw it again. Maybe this discussion may take a few extra minutes. So did somebody have any other questions? Somebody was asking another question. So that was more relevant to this discussion.
Vishal was asking.
Vishal,
Hello, sir.
Yeah.
So I was asking, why is epsilon taken into account for lambda VV?
Why does epsilon?
It's taken into account for calculating lambda VV, sir.
In both, in fact, lambda VV as well as lambda. Yeah. So that is basically, again, to have the same effect. So this is not about local buckling so much. You have seen epsilon being used for local buckling before. But here, basically, it is saying that this is the buckling capacity. Okay. Lambda corresponds to a buckling capacity. But this equation has been developed, or this kind of because this is a very empirical kind of an equation which is used here, lambda E. Right? You can see this lambda E equation which uses K1, K2, K3. So this might have been developed for Fy is equal to 20. Sorry, Fy is equal to 250 for other Fy values. Since they did not develop it, so they wanted to avoid a situation where pure elastic buckling type of a failure takes place before the yielding occurs, and that's why they have adopted an epsilon. So similar concept as in local buckling.
Okay.
Yeah. Coming back to this question then, tubular sections can be used. I have seen tubular sections being used in towers, telecom towers. I have seen their use in these roof trusses of high important structures. So I have never seen them in the industrial buildings. I have seen them at airports, and I have seen them in stadia. Okay, and I have seen the use of tubular sections, and I'm talking about hollow tubular sections only, not the concrete filled kind. Where else have I seen them? Offshore structures. So again, offshore structures are of very high value structures. So such kind of important, so these two are usually high importance, high aesthetic. So these roof trusses, typically the architect governs. The architects wants them to be very aesthetically pleasing. So therefore, tubular sections are the winners. Angles will look ugly. right? Or I sections will look ugly with so many corners and edges. So tubular sections look very pretty. So that's why they go for these. What they have to do is, if you have a big tube, let's say, usually one kind of system I have seen often is that they have 3 tubes. This kind of a 3-tube system where the braces are provided this way, and these braces are even tubes sometimes, and there will be a weld between these braces. So all this welding is done not at site but in a factory. So in a factory they can do it in a very good detail. Yeah. So if imagine that the major tube is here and one tube is coming from, one brace is coming at a very weird angle, whatever angle it could be. It is a 3D truss. So this angle can be very complex, but all this mathematically it can be modeled, can be developed. The tube can be cut in perfect shape, and then welding can be done through a robotic arm in a perfect shape. Okay, so this kind of applications are used here. Similar kind of a thing is done in offshore structures also. Offshore structures also have heavy tubes. There the efficiency matters. Also, the approach in offshore structures. Can anybody tell me why they use hollow tubes in offshore structures? Offshore, you understand, right?
Yes, sir.
They are submerged into water.
Yes, yes.
Yeah. Why would they prefer to use hollow sections? It is quite intuitive, actually.
Maybe due to mass, less.
Mass, I mean, like how much 10% gain you can get in mass? 20%. Harish, you had something to say?
Same. Water pressure. Water pressure exerted on the uniform.
Yeah, Sadullah. So yeah, so I don't know what you exactly meant by water pressure, but yeah, it has got something to do with water. So what happens is that hollow sections, they make the entire truss. Let's say they had let's say this was a 4-legged truss, okay, of an offshore structure, which had some bracings, etc. Now, these major pipes are these, and also these are also pipes. Okay. They are all welded together at the site. And what they do is they keep some caps here in these pipes. These caps can be opened and closed as they wish. Then what happens is that these structures are sometimes 60 meters, 70 meter long, and putting them on a boat becomes a huge challenge. You have to get a boat of that size and putting on a boat. But funny thing is that these hollow sections are such that if you calculate the area of steel versus hollow area inside, you will see that hollow area inside is 7-8 times greater than the steel area, which basically means that if you have a water pressure acting on this one from all sides, it will float. The steel pipe will float as long as water does not get inside. Okay, if you have air inside, then the pipe will float in water. So they need to take it to the offshore location, which may be like 20 kilometers, 30 kilometers deep. By deep I mean into the ocean, away from the shore. So they build the whole thing at the shore, most of the truss. Then they plug these holes temporarily. They throw it in water, like throw it slowly, okay, and then they pull it so it is floating in water on its own, and then they tug it with a boat. Then they don't need a huge boat to carry it because it is floating on its own. They don't need a boat to support the weight of this thing. It is floating, and with a very small force they can pull it to whatever distance they need to. After they get there, then they start opening these valves strategically in such a way so that when they are taking this truss to the site, the truss is horizontal. Okay, it is placed like this, submerged half into water. Okay, once it gets to the site, then they start opening these valves one by one in such a way, and that simulation is done beforehand. They know which valves to be opened at what time, so that water starts getting into these pipes, and then the pipe starts to sink, or the structure starts to sink in a proper way so that its orientation is proper. So slowly it starts to go this way, and then this way, and so on, and it orients itself properly and then goes down. Then of course they have to tie some anchors to the ground from various corners and then pull it so that you can adjust it accordingly. So that is a special application where they use, and that there having a hollow section helps. And there too, welding is the primary mode of connections. So connection issues are handled here this way. In telecom towers, the connections are of slightly different kind. In telecom towers, you have tubular columns, or main legs are tubular. Again, I would recommend those when you come back to the campus, look at the Reliance Tower near the canteen area outside the campus, but it is right at the corner. So the main legs will typically be your tubes, okay? And then you have to do the splicing between the main legs. Other than that, you don't need much connection. So the splicing is typically done with an end plate kind of a connection. So you have a tube, the tube is pre-welded with an end plate, which has some 6 or 5 holes or 4 holes, something like that. Then there is another pipe with another end plate connected to it, which also has these holes at the same location. You put them together and you put bolts through it. So these are basically bolted connections. That's how you do the splicing. Other than that, you don't need any other connections on the main members. The main members are all continuous. Then comes the question of how do you connect the braces to these members. Then there are 2 different approaches which are adopted. Either you can go for an angle. So what they do is, this is the main leg. They can weld a small gusset plate to this leg. It is welded, okay? And then you bring an angle and bolt it, okay? That is a more common approach. Alternatively, what they do is, they again put a gusset plate, weld it, and instead of an angle, they bring another tube. But at the ends, the tube is crimped, okay? So it becomes flatter and wider, and then bolted. So this kind of a crimped ends are useful or can be used only in case of a for members which are not a very large size and they have enough ductility or small deformations only. So this kind of arrangement can be done. So basically what happens is that tube ends are flatter. It's exaggerated view, of course. So here it is a round section, but at the ends you flatten it. Okay. So and here you can put a bolt through 2 layers of steel. Okay. So this kind of an arrangement is typically done for small telecom towers, not something very serious, something very big. So 40 meters, 30 meters, 25 meters, this kind of an arrangement is acceptable. Okay. So connection for tubular members is a huge challenge, and that is why they are not still very popular. But as welding is picking up more as a connecting options, now you have many more venues open. So again, those who have been to IIT campus, if you look at academic block B, it is all made of tubular members. But the tubular members, the funny thing is that the way they have designed these tubular members, these are not ready-made tubes available in the market. They have used 4 plates to make a tube. That's a different story. We will spend some other time someday to discuss that. Okay. All right, Lohit, I answered your question or not?
Yes, sir. Yes, perfectly. Thank you.
Okay, fine. All right. Any other questions? We have 3 minutes to go. Otherwise, I can let you go 3 minutes sooner. Okay, then. All right. We'll see you on Thursday. Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir. Bye.
Thank you, sir.
Thank you, sir.